Welcome to Study Loop.
This is problem 52 of chapter 23. In this problem, we are evaluating single slit diffraction with sound. So let's recall the single slit diffraction equation. W for the width of the slit, sine of theta m, where theta is the angle to a diffraction minimum and m is the order of that diffraction, is equal to m lambda, where lambda is the wavelength of the wave. So here we are dealing with sound, so the speed of sound, v sub s, is equal to 340 meters per second. And this is going to be equal to lambda f. We are given the angle of the first diffraction minimum here. So the angle theta 1 is given as 45 degrees. And we are asked to solve for the width when different frequencies of sound are used. So here, let's go ahead and solve this equation for the width. Width W is just going to be equal to m lambda over sine of theta m. For our specific problem, m is just going to be equal to 1. So let's go ahead and write that. W is going to be equal to 1 times lambda, well that's just lambda, over sine of theta 1, which is 45 degrees. What's going to change is the frequency. So here, let's go ahead and substitute for lambda. According to this expression, lambda is going to be equal to the speed of sound divided by the frequency. So we'll go ahead and substitute this quantity, Vs over F, for lambda. Sine of theta 1, well that's just sine of 45 degrees. So this is just going to be sine of 45 degrees. There's our frequency, and then here the speed of sound is 340 meters per second. So meters per second, this inverse second is going to cancel out with the units for frequency, which is inverse seconds or hertz. So our answer here is going to be in meters once we plug everything in. Okay, we're given 3 cases. Part A says solve this when the frequency is 2 hertz. So frequency is 200 hertz. So let's go ahead and solve for this W. So W is going to be equal to this expression, and all we have to do is change the frequency. So let's go ahead and copy this, paste it here. All we have to do is change the frequency. This is going to be to 200 hertz. This is going to be multiplication here. So let's put a bullet here. So it's going to be sine of 45 times 200 in the denominator. So this comes out to be 2.4 meters for part A. Okay, let's do part B. Part B is going to be very similar. All that changes is the frequency. Frequency is 1000 hertz. So all we have to do is copy this expression here. Let's just put the bullet here. Symbolize a product. Let's just copy this, and let's solve for this width. All that's changing is this frequency here in the denominator, and that's 1000 hertz. When we multiply this out, we get 0.48 meters. Okay, the last frequency we're given, so it's going to be part C. The last frequency is 10,000 hertz. So let's go ahead and plug that into this expression here. All we have to change is the frequency. So W is going to be equal to this expression. All we're going to do is change the frequency here. It's going to be 10,000 Hertz. And this comes out to 0.048 meters. So here we see that as the frequency increases, the opening of the stereo, which resembles a slit, must decrease. So as the frequency increases, the slit width must decrease such that that first diffraction minimum occurs at 45 degrees. So this concludes problem 52.